Guys. Yeah, my name is Brett Mullins. Been with Disney-McLane for about 17 years. Like Jim said, we also have Jim Hoover on board. Jim is the regional sales manager for our territory, among many others. So today we're going to be covering water heater efficiencies, mainly geared towards high efficient. We'll be going over basic construction of the water heaters along with the materials that are used inside of them. We have installation conditions that we're going to be covering, and then we're also going to compare that with some other water heating options that you guys have with regard to their piping and field conditions and efficiencies that are related to that. And then after we cover all that, I also want to cover not only gas is a water heat source, but also cover steam and then boiler water. We're going to cover a sizing program specifically for steam, where we could couple steam heat exchangers with stored, like actual stored water heating. So as we get into this sucker. All right, so as we sit there and use natural gas is our fuel. One of the byproducts of that is CO2 and then along with some water. So that's a condition that's always going to be there no matter what type of gas water heater we use. So there's basically two types. We have a non-condensing and a condensing water heater. The difference between them is going to be the efficiencies. So as we look at how those thermal efficiencies are garnered. Basically, if you look at the equation, we're looking at our output divided by the input. So you're taking the BTU and the electricity that we're putting into that water heater, and you're going to judge that by the temperature of the water we get out. So it's a very basic equation, and that's governed by ANSY's E21.10.3. And the test itself is the same no matter what type of heater it is, or boiler for that matter, whether it's 70 degrees coming in and you cannot deviate by plus or minus 2 degrees on a 140 outlet. So the test duration's for 30 minutes, and then afterwards is where they get all that information, and that's how they come up with the thermal efficiency. So anything above 84% and your efficiency is classified as condensing. Anything below is non-condensing. There are different requirements for other locations like Canada, for instance, which was shown on that slide. So in a non-condensing water heater, the burner assembly is going to be on the bottom of the unit, and it actually travels up through the water inside the tank. So the downside of that is the coldest flue is next to the hottest water. So it's an upflow on the actual flue gases. And so we're not scrubbing as much heat off of that system, which is why it's non-condensing. So instead of having all the heat go into the water, we have a lot of heat going up the vent stack, that's why the vent stack is at such a higher temperature. Because if it was a higher efficient unit, we wouldn't be losing as much heat up the vent, it'd be going into the water. But because the vent temperatures are so hot, it is naturally buoyant. So we don't really need to have that extra push of a blower or anything like that to get the flue gases out of that system. With regard to a condensing water heater, the burner assembly is traditionally on top. So we force that flame down. And what that's going to do is you have the coldest water surrounding the coldest flue gas, so it's an upflow. So what that does, it allows us to scrub more heat off of that system and into the water. So when we do that, since we're scrubbing so much heat off of it, if you remember anytime we burn methane or natural gas, some of the products are water and then also carbon dioxide. So, and that's going to give you your condensate. The carbon dioxide is going to make that more acidic. And then also because it loses so much heat, it loses some of that buoyancy. So we've got to put a little push behind the system with a blower. And then so that's how the basic construction of a condensing water heater is arranged. Because of that condensate that we create, the products that the water heaters are made out of different materials to combat the more aggressive nature of the condensate that we just created. So condensate's traditionally between 2.5 and 5 on the pH scale. It's pretty acidic. So not only do we need to look at some different materials that we need to construct the heaters out of, but we also need to take some other considerations into play with regard to how we treat that condensate before we throw it down a drain. And that's also why we need like a condensate neutralization tank, which is shown in the bottom right-hand corner. So what that does is it basically takes that condensate, neutralizes it so it doesn't attack our drain system. Like if we have, for instance, cast iron drains, they wouldn't last too long if we were throwing a pH level of a 2.5 down the system. So the other aspect of condensing water heater is applications are the vent materials. So yes, it's a lower temperature, but it's also more corrosive. So because it's a lower temperature, we are able to use more of a poly-type construction material for our venting, which would be like your PVC, CPVC, or polypropylene. But those units also don't take heat very well, so we have to be cognizant of how efficient our heating systems are working because we're using that type of vent material, which won't be able to handle that higher heat. Excuse me. So historically, natural gas is not that expensive. So with regard to that, we're looking at payback with the cost of a high efficient unit versus the cost of a non-condensing unit. So 80% of the heaters out there sold a replacement, and the majority of them are still in a non-condensing type format. Now PVI, which is our manufacturer, is different. We take a different approach to things than traditional water heaters. So our market segments are still predominantly new construction versus replacement, and there's a few different reasons why, which we'll cover here in a short period of time. But if the life expectancy of that condensing water heater is short, you're really not going to utilize the payback for the added cost that it goes into manufacturing that high efficient unit because of the other installation requirements that go into installing the high efficient, and then also just the materials that it requires to manufacture it. So most condensing water heaters are, their thermal efficiency is somewhere between 95 and 98%. So they are much more efficient than non-condensing, but just looking at a payback scenario, this example, so a non-condensing unit with 400,000 BTUs with 4 hours a day of operation is going to cost you, a little over $3,000 a year. The efficiencies that you're going to save in fuel cost is going to knock that down if you went with a condensing unit to just above $2,400 a year. So judging from the difference between the non-condensing and condensing, we're looking at around $800 a year. So we're saving 30% more, but we're going to need to at least have 4 years of life to justify the added expense of putting that non-condensing unit in there. If you get less than that, then really the total cost of ownership might have been more beneficial to go with a condensing or a non-condensing unit. So with regard to the way we heat water, one of the main variables is obviously the water that we're using. So water is known as the universal solvent. It's something we have to play with. And with regard to where our installations are, water changes all over the place. So traditionally in our footprint, which is going to be Ohio, Kentucky, Indiana, we have pretty hard water. Which means that there's going to be a lot of dissolved minerals in the water, which is going to change a lot of aspects of efficiency if we don't maintain and kind of accrue for that additional hardness and scale that's going to be prevalent in our systems. So when water is heated, basically it undergoes a chemical reaction, and some of the things, like all those dissolved solids that we were talking about, when we heat it, it becomes more aggressive, and they're going to precipitate out, and that precipitation is scale. So what that's also going to do is it's going to make the water more conductive, more aggressive, and it's also, as a byproduct, going to push off from the water into the rest of the system oxygen and carbon dioxide, which is a natural byproduct of that reaction. So with scale, it can, obviously, we all deal with it. So scale's prevalent in almost every situation we come into. And there's a few different ways that we can combat it. You can do it with ion exchange or water softeners. You can do it with some products have like magnetic fields where they try and change the polarity of the ions to make them, basically neuter them. You can do reverse osmosis, which there's a lot of water waste in that type of situation, and for larger type volume applications is not really feasible. But there's a few other methods that we can also use to combat scale. But looking at the chart at the bottom, you can see as the temperature increases, you can see how much more scale is built out of that system. Every time you increase the water, I think you basically increase your scale production by 25%. So, which is going to inversely affect our efficiencies of our system. So this chart, you'll see how you lose efficiency depending on the thickness of the scale that's built up inside your system. So on the left side, it's just 1/64th. You're going to lose about 5% efficiency. And then if you have 3/4 inches of scale built up in your system, we're losing them as 90% efficiency in that system. What that basically means is all the heat that we're creating has to go through not only the tank wall, but then also the extra thickness of the scale that's inside that system. It just can't get through it. So since we're not able to scrub off any of that heat, it's all going to go up the vent stack, and we're just losing all of that out to basically atmosphere. So another thing that happens with water is, especially if you heat it, is additional corrosion. So not only are we building scale, but also makes it more aggressive and more corrosive. So every time you heat water, you're going to have oxygen and carbon dioxide as a byproduct. The other aspect of it is electrolysis that can come into play. So you have all those dissolved solids in the water. You have different tank or different metallic components in the system. That's essentially creating a battery. So you have your cathode, your anode, and then your water is going to be your electrolyte. In traditional water heaters that are made of carbon steel, they're going to line those systems. And that's also true with stainless, but just to a little bit of a lesser degree. We don't have a traditional lining. So basically what they do in order to protect that anode, which is going to be the carbon steel tank, they surround it with a tank lining. There's a few different tank lining materials that are used. There's different ways that people do it. But your cathode is going to be your other metallic system, your copper piping, your heat exchanger, that type of stuff. And then your anode is going to be your carbon steel tank. And then your water is going to be your electrolyte, which is going to complete that triangle. So anytime you have an anode, a cathode, and electrolyte, you're going to get corrosion. So, and what's going to happen is traditionally the carbon steel tank is going to sacrifice itself in that triangle. It's going to give up all of its electrons in that system and basically erode. So in order to combat that, what manufacturers do, if they don't have a complete 100% lining of that tank or metallic materials inside that tank, they use anode rods. So traditionally, people will say a glass-lined tank. What that actually is like a porcelain enamel. So they basically they make the inner lining a glass, okay? So that is probably 90% of the carbon steel tanks out there. That's the type of material that they use, or that's the type of process they use in order to protect that carbon steel inside of it, is they basically coat it with a porcelain enamel or glass. There's other tank linings as well. Here's a list of them. So you have cement, glass, epoxy, thermoplastic, and then metal plating. So, you know, some of them will require anode rods, some won't. The thermoplastic or metal plating, like a nickel plating or something like that, would not require an anode rod. The epoxy, the glass, and the cement still does. But their warranties are, you know, correlated to that as well. So cement can get up to a 20-year warranty, but it's also extremely heavy, and it's harder to it's harder to move around. You can't recycle it, and so that's why a lot of people went with glass, because not only is it's just a lot less to manufacture that way. So with the anode rods that are installed in there, basically they're made out of magnesium and aluminum. And if you look at the electrode potential up in the top right, you'll see why it's used. It's because they're very sacrificial. They want to give up their electrons, which is why they're used. So basically, if you have a tank that has anode rods in it, they're there to protect the tank. It's because they are sacrificing themselves in lieu of that carbon steel that's present inside that system. So, but there's some other design aspects of anode rods that need to be taken into consideration. So there's something called shadowing. If you have vertical fire tubes inside that tank, the tank itself has to have line of sight to that anode rod for that anode rod to function properly. So if for some reason those anode rods are tucked behind some fire tubes and there's a shadow casted on the side wall of that tank is going to be unprotected. That section of that tank will be unprotected. Because it doesn't have direct line of sight, it won't be able to sacrifice itself and protect that side of the tank. And it's also true with distance. So if they only have one or two anode rods in it, the closer you are to that substance or material, the more protection that anode rod is going to give you for that system, which needs to be taken into consideration with design of water heaters and anode rods in general. And with the more fire tubes you throw into a system, the more heat transfer you get. If you're using anode rods, you're also going to have a lot more shadows cast on the side walls of that tank. So unlined materials, so like with any metal, you know, they're going to get some passive layer. With carbon steel, it's going to be rust. You're going to get, you know, a rust layer, just like you would with any other carbon type based metal. With stainless steel, it's actually a chromium oxide, which is kind of the rust equivalent to stainless steel. Basically, it's trying to protect itself, and that's how it does it. There's a bunch of different kinds of grades of stainless steel. They are not all equal. They're not all conducive to domestic water heating. And we'll cover that right here. So austenitic stainless steel, this is traditionally described as like your 300 grade stainless steel. This is the majority of the stainless steel that's used in manufacturing. And there's a few different reasons why. One, it's less expensive. But two, it's easier to work with. You can bend it, you can mold it, you can weld it, you can work with it. And that's why a lot of manufacturers like to use it. But the downside of it is it doesn't protect against, it's not very resistant to salts. And what salts correlate to are chlorides. So, and obviously with domestic water, it's going to have chlorine in it. And that's also true with regard to scale. The same is true with chlorides. The more we heat it, the more aggressive it becomes. So with 300 grade, it's really less expensive and easy to work with, but it doesn't always work very well for domestic water heating applications. And one of the reasons why for the longest time, ASME code would not allow 300 grade stainless is because of that. It's because it didn't work well under chlorine conditions. So that changed recently within the past few years, where especially it came down to boiler manufacturers that had a bunch of 300 grade stainless because they were traditionally used on hydronic applications. They wanted to use that in domestic water applications as well, and they didn't want to make a different heat exchanger. So as the codes were updated, one of the things that came through with allowing 300 grade is now the engineers are responsible for the material, which needs to be taken under consideration for the longevity of the system. So the other type of stainless is ferritic. Ferritic is going to be your 400 grade stainless. 400 grade stainless is it's harder, it's slightly more brittle because of that, but it's very good at protecting itself against stress chloride cracking. It actually does an extremely good job of protecting itself against the salt and chlorides in that system. So it's more complicated to manufacture with it, but for a domestic application, it protects itself a lot better, which is why in the past 400 grade was the only thing allowed under ASME code for that hot water heater type certification. Another thing is because it's so much harder to work with, it's harder to make larger pieces of equipment out of it. It's harder to, you're welding a bunch of stuff together, and it's much harder to make one monolithic type of a piece out of 400 grade than it is stainless, or 300 grade stainless. So one thing that you can do is you can actually do an alloy between the two different types of stainless steel. So we have our austenite and our ferrite, which is going to be your 300 and 400 grade. This is a 50-50 alloy, so you have a 50% ferritic and 50% austenitic. The trade name for this type of alloy is LDX2101. So it's 21% chromium and 1% nickel. So there's a very minimum amount of carbon in this alloy. And basically what this does is it takes all the benefits and features of 300 grade with regard to being able to manufacture it, mold it, and control it, and then also incorporating the added benefits of ferritic, which is going to be your subversion to stress chloride cracking in a domestic water heating type situation. Now PVI calls this Aquaplex, that's a trade name for it, but basically it is the alloy LDX2101. So with regard to that, there's some manufacturing practices that need to be taken into consideration if you're going to be using this type of material. You have to be able to weld it. You have to be able to work with it. You have to be able to passivate it after it's all done, and that's not an easy thing to do. So some of the considerations that need to be taken into play is with regard to crevices, no crevices, welding, things like that. So for ASME construction, you're not allowed to have a crevice in that system. And what a crevice is described as is basically a void in the material that's 2 times the diameter as the width. That is the technical description of a crevice. So with no crevice, what that does is it doesn't allow an imperfection in the tank itself to where some corrosion can start. So it allows water and oxygen and everything else that we'll actually need in order to passivate that tank into that crevice, or into that void, which is that no crevice down the bottom right. So when you make things with LDX2101 or Aquaplex, the bottom right-hand picture is that shows what it looks like after you cut it, weld it, put that tank together. So in order to bring that thing back to its natural state, you do need to pickle and passivate it. And what PVI does is they actually immerse it in 4% hydrofluoric and 20% nitric acid. They do it at an elevated temperature for an hour. And what that does is it removes all of the imperfections that were created during the manufacturing process. it restores that 50-50 austenitic and phoretic ratio inside the system, including the welds. And the nice thing from a domestic water heating application standpoint is the water that's inside those tanks will reoxidize and recreate that chromium oxidized layer, which is what we use to protect it. So even, the water going through this system is going to continue to passivate it after it's been installed. And here's a picture of the weld, and then also the after the pickling and passivation, what it looks like. So this makes the entire tank protected against stress chloride cracking. It's very corrosion resistant. And this tank picture itself is actually after it's been in use. So I'm going to show you another picture, and this is going to show you why you use either 400 grade or an LDX 2101 duplex stainless steel type alloy in a domestic water heating application versus 300 grade. So, but you have to be able to, it's the process of manufacturing it, not just the material. And this is a picture of the exact same test with a 300 grade. Same duration, same water, same temperatures, same everything. So that's why 300 grade stainless is not traditionally been accepted in water heating applications, and 400 grade was, is because of the water attacking that 300 grade, and basically the chlorine and chlorides in the system attacking that 300 grade stainless. So it's specifically designed for potable water. Everything that PVI makes is ASME constructed, and it's specifically designed for the applications that you guys are going to be putting it into. But not only do they have the material, they have the access to the technology to cutting it, welding it, and then most, or not equally as important, is the ability to pickle it and passivate it with that hydrofluoric and nitric acid bath. So with that, and you can have much larger warranty periods. So with a vertical fire tube type design, you're looking at a 15-year warranty as a standard offering. With what we call our super tank design, we'll give you a 25-year warranty. Basically what that is it's a tank which has a 23-inch manway that we can incorporate different heat sources in the heat exchanger into it, but it can be removed so we can have access to the inner part of the tank. So not only are our tank materials made out of it, but also our heat exchangers are made out of it as well. So getting back to the basics of what thermal efficiency is, like we stated previously, it's basically we're taking all of our input, everything that we throw into that heat source, we do the exact same test, and we find out what we get out of it, we put it into the equation, and that's where we get our thermal efficiency. Excuse me. So one of the variables into that is the 70 degrees coming into it and the 140 degrees going out of it. The test itself is steady, so we're always feeding it 70 degrees. We're always pulling 140 degrees out of it, so that does not change. But what that means is our field conditions, it's very hard to replicate that test because we don't always feed our water heaters with 70-degree water. And that's also, we'll talk about that here and extensively coming up. So here's all of the different factors that go into what makes a water heater efficient. And the most important one is actually the return water temperature. That's the greatest influence that we have coming into that equation. And the reason why is because the hotter the water coming into it, the less heat we can put into it. So if we feed it as cold a water as possible, that means we can put more heat into that water, which is where we're going to gain our efficiencies. There's a standard chart that you're going to see. This is very common across all different condensing and non-condensing boiler type designs. So everything on the left side with the speckled gray area is going to be your condensing zone. So basically what's going to happen is your return water or the water you're feeding into that system increases. You're going to hit the dew point eventually, and it's not going to condense anymore. And so everything you're throwing up the stack at that point is going to be much higher temperature, and your water heater is no longer condensing at all because the it just can't do it. It's physically impossible because of the water temperature we're giving it. So this shows exactly where, you know, that equation is derived from. So that 70-degree point is further on the left side of that chart. And that's also why on those tests, a lot of the manufacturers can say, especially boiler-type manufacturers, can say that they're in the upper 90% efficiencies because they're feeding it that 70-degree incoming water for that test. So another, as we start comparing other heating options and sources, another thing that comes up all the time is tankless water heaters. So tankless water heaters are sold as a high-efficient system. You're not heating water that we're storing or not using, but they go through the exact same test process in order to garner their efficiencies. So, but one thing to be said of it is tankless water heaters will sacrifice hot water output in order to maintain temperature. So as you use a tankless water heater in your system, it's very the incoming water temperature is very important to these. So the output or the efficiencies you're going to get out of a tankless water heater are going to be drastically different, or performance of a tankless water heater is going to be drastically different in colder weather versus warmer weather. So in most of our commercial type designs, we're going to be using a recirc pump. I believe that's a standard now where you can't even have dead legs anywhere, so we have to be able to bring that water back. And what's going to happen is we're basically preheating our water that we're throwing into that tankless water heater. So looking at it, even if you couple with a storage tank or the rest of the system, you're preheating your water that you're feeding that tankless water heater. So we're no longer giving it 70 degrees. It's at a much higher temperature. So especially with a hot water storage tank, if we're close to that, your incoming water temperature is going to be drastically higher. So one of the main arguments for tankless is standby loss. And with regards to the R value of the insulation that are now required in water heaters, the standby loss or heat loss is much less than what it was in the past. And so our standby loss heat formula shown at the bottom of the page is basically you take your input and then you put it into that equation. That's going to give you how much you're going to lose over a period of time. So in a standard type example, so here we have 1.2 million BTU system with a 125-gallon storage tank. So at 7 hours a day of operation, we have 17 hours of standby, and for an entire year. If you pay 75 cents per therm, or 90 cents per therm at 75 therms per year, basically you're saving $67 dollars. So it's really not that much. You're only losing $67 in that tank, which is going to equate about to a third of a percent of the annual cost of fuel consumption, which is minimal. So really, if you look at it, the argument of standby loss versus tankless, we're talking about 0.003% of that annual fuel cost.
Hey, Brett?
Yes, sir.
This is Jim Hoover. I would like to add to that one of the misconceptions out there is that when you install a storage water heater, the standby loss has not been calculated into the efficiency test, and it is. It's the second part of the efficiency test. So when we're giving you the efficiency rating third-party certification on a storage water heater, that already includes the standby loss. There's no additional losses that are going to be incurred just by putting a storage water heater in. So if you're 95% efficient, that includes the standby loss calculation.
That's a very good point, Jim. Thank you. So as we up the BTUs and also increase the gallons of storage, you're going to lose more therms per year. So we're at 1.8 million on this system. We doubled the storage of 250 gallons. And even by doing that, we only increased the therms lost minimally. So now we're looking at 0.2%, or 0.0043% of an annual fuel consumption. So even by bringing more of that stored water heater or stored water into that system, the difference in thermal loss is just really minimized. So as we said before, with regard to incoming water going into a tankless, that's the most important factor for their thermal efficiency. And that's also where they judge how much water they're able to put out. So this is taken right out of a tankless water heater design and installation guide. You can see where it's certified at 10.2 gallons per minute at a 70-degree rise. But that's with the 70-degree incoming water temperature. We very rarely have that. So most of the time our water temperature is going to be much less. So, you know, as that thing's sacrificing its flow rate to maintain temperature, that's also where you're getting your pressure loss in that system. So let's say it's a hotel, for instance, and you might be racking up a few of them. You know, your pressure loss, especially in the wintertime versus summertime, is going to be drastically different in that system. So that's also going to affect your showers. That's also going to affect if you have thermal or thermostatic mixing valves in that system. They have to be within a certain range of pressure on the cold and hot incoming into those valves in order for those to function properly. So we've ran into a few headache scenarios where the mixing valve performance is drastically affected by the tankless water heaters installed in that system, and it changes seasonally. So the other thing too is when it comes to gas piping. So lining up a bunch of tankless water heaters, you're going to have to run a bunch of gas to it, and you wouldn't need to have as large a gas piping 1 to 2 tank type heaters. So in this scenario, you actually have to bump it up from 2.5 to 3 to get the same amount of BTUs out of that system. You can rack them. They can prefab tankless water heaters into a skid type system. But another thing that needs to be taken into consideration is the venting and the complexity of it. So now a lot of tankless water heaters are actually coupling their tankless water heaters with storage. So, and that's for more commercial type applications, obviously. But one thing that needs to be said is the maintenance of the tankless water heater would still apply. So you're still going to have a very tight flow path going through that heat exchanger, which is very it becomes very prevalent in hot or in hard water type applications. There's a pretty steady preventative maintenance type scheduling that needs to be in place from a best management practice of that facility in order to protect those heat exchangers. So that does not change no matter what you put in that system with regard to storage or non-storage with tankless water heaters. So going back to our chart again, so it's the same exact chart. Like we said before, the return water temperature is by far the most important variable into that equation. Like Jim said, with a water heater, all of that is taken into consideration when we certify these things to a certain efficiency. So here's a generalized piping diagram of a water heater type installation. This is a reverse return type setup. It's first in, first out, or first in, last out, sorry. So it's a very easy way to balance the system so you're not pulling out of one water heater versus the other. It's very, from an installation point of view, it's very simplified. We can couple that with storage tanks. So let's say you need minimal recovery with a larger storage capacity for a certain dump load. We can easily install them that way. It's still a very basic type piping diagram. We would just have interconnected piping with dedicated pumps to each water heater into the storage tank to turn those things over and keep the temperature uniform. With regards to boiler efficiencies, like Jim said before, that piece of equipment is what's certified to that ANSI Z21.10.3. So whatever efficiency is derived from that equation, it's from that piece of equipment. With the water heater, that piece of equipment includes the storage. It includes the tank. It includes the insulation, the standby loss, everything. With a boiler, it includes just the boiler. So it doesn't include all those other variables that would come into a standard type field application. So with that ANSI standard, this is how usually a boiler tank would be installed into a system. So the certified boiler over there on the left is going to be installed with a storage tank in order to have some buffer inside that system for multiple reasons. So one, it's going to give you a dump load capability, but the other thing too is that heat exchanger that are inside those boilers, they have to be protected. So the way that they're protected is with flow. So basically what that means is the less demand, that's going to mean that that heat exchanger needs to get flow from somewhere. So for instance, if a building only needs 3 to 5 GPM of hot water, but that heat exchanger inside that boiler requires 20 GPM in order to protect it so it doesn't overheat, it's getting that other 15 GPM from that storage water tank, which is stored at 140 degrees. So with us taking that 15 GPM out of that tank, pre-mixing it and throwing it through that heat exchanger, we are no longer feeding it with the coldest temperature as possible under those low flow or low demand type situations. And that's why under those low demand situations we have a lower efficiency of that boiler, because we're not feeding it 70-degree water anymore. We're probably feeding it closer to 120, 115 at best, if not even higher. If that storage tank's stored at 140, we could be giving 136 degrees right into that heat exchanger. So in those type of situations, it's physically impossible for those boilers to condense. The other thing that needs to be taken into consideration is all the additional piping and pumps, and along with the pumps, the electricity that's used in order to, in order for that system to be installed properly. So the piping is a little more convoluted, a little more flow dependent to protect those heat exchangers. For instance, if the facilities maintenance guy replaces a pump in that system that's not designed for that heat exchanger, then he could be burning through heat exchangers because it's not flowing enough. Or he could be eroding the heat exchangers because it's flowing too much. So when you take a look at the boiler tank efficiency curve, this is basically how they, judge their efficiency. So they're going to sit there and say they're at 96% efficient. But if you look at the entire flow dynamics of how efficient they're going to be in the field, it's very hard for them to replicate that. And that's due to what we just talked about before with the incoming water temperature. If you remember, the incoming water temperature is the largest variable or the most important variable in that equation. And so when you factor that into it, it drops their efficiencies. And if you add all the other components into that system, it actually derates their efficiencies by a usually average of about 4%. So that's something that we definitely need to take in consideration when we're designing or talking to owners, is be able to communicate exactly what those efficiencies mean and how it's going to be applicable for their building. Some other things, too, that also need to be taken into consideration is some boiler manufacturers, they actually derate their efficiencies based on their vent lengths. So certain boiler manufacturers will derate their efficiency by upwards of 4% for every 25 equivalent feet of their venting. So that's also important to take a look at. So as we said before, it's very important to have everything in line for a boiler tank design. Everything has to work together. It's more complicated. There's a lot more standby loss because of the piping, which they cannot take into consideration for their efficiency equations. So here's the difference between those piping diagrams. So top right, tank design, bottom left, boiler tank design, and there's also a lot of additional installation costs that would be accrued because of that. So going over a gas water heater offering with PVI, we do have condensing, non-condensing, natural and LP, and also low NOx units. Like we said before, everything's made out of ASME construction. You know, we pressure test at 1.5 times design, and this is why you do it. So what ASME versus non-ASME, there's a big difference in the quality of weld. I probably don't need to explain that to you guys. You guys probably are well aware of that. But we do see quite often a bunch of non-ASME type tanks going into commercial water heating. And, you know, it's basically a residential unit that we're slapping into a commercial water heating situation. And that's what can happen because of the lack of control or lack of importance of focusing on the welds and everything else. So some of the pictures that you've been seeing, that's our Conquest unit. We can go from 200 to 1 million BTUs. 299 and under would be 100 gallons. 399 and above is going to be 130 gallons. So at full fire, if you remember our efficiency curve, you know, we're at 96%. And that does not, our flow conditions do not affect our efficiency rating. So if you're flowing 1 gallon a minute or you're flowing 50 gallons a minute, 100 gallons a minute, our efficiency rating would stay the same. Under part load, you know, smaller loads, we actually increase up to 99%. So here's a picture of the smaller, the 100-gallon heat exchanger. You'll see it's a vertical fire tube design. They're actually, if you notice, the fire tubes are crimped, and what that's there for is to slow down that fuel or that our combustion there, in order to scrub all the heat as possible into that water. So if those were just full open tubes, the actual the heat would travel too fast through those tubes to scrub off into that water. So that's why we slow it down with those with that crimping. Now on the larger tanks, 130-gallon tanks, it's more of a spiral type heat exchanger design. It's still a single pass, which is very important when it comes to the acoustics of it. And the reason why is because certain manufacturers, they would have more of a baffling type setup where they have vertical fire tubes, but they redirect that heat and that flue 3 different times in order to scrub as much heat off of it as possible. But because they have to push so much air and heat through those heat exchangers, they have to have a very large blower to accommodate that. With this being a single pass design, our blower doesn't have to be nearly as large, which means it's a lot quieter. So for hotels type situations where the acoustics of it might be a detriment on the aesthetics for you know, hotel owners, that's a very important attribute that a single pass design has versus a multi-pass design heat exchanger. So another thing that you'll notice with these type of designs is our return fitting is at a midway point on our tanks. If you remember on the boiler tank design or any other manufacturer of water heaters, they actually they bring their building return into the cold water feed of their water heater or boiler, which is preheating the water going into the system. With us having a mid-tank return fitting, what we're doing is we're bringing that return water into the non-condensing zone of the heater. That's important because whatever water is used in that system, we're introducing as cold a water as possible inside that tank into the condensing zone. So that allows us to maintain those much higher efficiencies at minimal flow rates, because no matter what we use in that system, we are always introducing as cold a water as possible to make sure we scrub off as much heat as possible into that water. This will give you a snapshot through 800,000 BTUs or 800,000 BTU offering. We can go actually much higher equivalent feet on venting. We would just have to go with larger vent diameter on the sizes. We can also go with an offering of Power VTs or Power VTX. Is 96% efficient. We can also go up to 1 million BTUs on that one. The difference is we bump it up to 215 gallons of storage. But it will also go up to 99% at low fire. The Power VT Plus, we can also go up to 99%, but now we can go up to 2 million BTUs. We have 250 gallons of storage and 300 gallons of storage. With our Turbo 96, if you guys are familiar with our Turbo Power, this is where we have that super tank type design with a 23-inch manway on the side. You'll see our burner assembly going through horizontally into the side of the tank. So what that does is it allows us to pull the burner assembly out of that tank, maintain it, clean it, replace just the burner if we need to, replace just the heat exchanger if we need to, and that tank still remains installed. So with that, we have a 25-year warranty. We can go up to 1,500 gallons of storage, and we'll still give you that 90% efficiency. This is a really nice unit. We're basically able to take those really high recoveries with storage and put them into a single footprint. And then we have the only true 99% efficient unit. So this is the Turbo 99. We see some of these on government or military type applications where we have where they have to meet a certain spec for efficiencies. So this is a true 99%, the only true 99% thermally efficient rated water heater. We can go up to 2 million BTUs on that one and also up to 1,200 gallons of storage. So that covers everything with regard to high efficient water heaters when it comes to gas as being our fuel source. One thing that I also want to talk about is going to be steam. So we get a lot of questions about steam. You know, there's a lot of different design considerations that need to be taken when designing steam type water heaters. And we have options to do things slightly differently. So one of the units that we have is the trade name's COBREX on it. It's a different type of approach to maintain water temperature coming out of it than your traditional steam water heater because we do everything on the water side. So there's a lot of advantages that come to this, and we'll go over that. So some of the advantages are extremely small footprint. We don't have a steam valve. So what we'll do, as long as we have 15 pounds feeding that heat exchanger, and if it's above that, we just put a steam pressure reducing valve on it. But what we do is we feed 15 pounds at most, we can go down to 5 pounds into that heat exchanger, and we control the outlet water temperature based on redundant blending valves downstream of that heat exchanger. What that does is it gives us extremely consistent temperature control. It's a lot less expensive to maintain because we remove the very expensive and sometimes fickle steam control valves. And because we did that, they're a lot lighter. We can put them into an extremely small footprint. The heat exchanger inside the COBREX unit, the steam is actually in the tubes and water's in the shell. That's important for a bunch of reasons, especially if you get into adverse water quality conditions with hard or aggressive water. So we do have a double wall design. The double wall extends down just to the first plate. So after the first plate, it's a single wall. So if there's a breach in that outside wall, it'll accumulate in that interstice between the two plates, and there's actually an atmospheric port that's on the side of the heat exchanger that would give you a visual indication that something's wrong with that heat exchanger. So that's a really nice thing for especially facility maintenance guys to have because it gives them a heads up that something's wrong. and they'll be able to kind of plan accordingly to get that fixed. So here's the basic diagram of how the system works. We're feeding steam into the tube inside that heat exchanger. We have an upflow with regard to the water, so we're feeding extremely cold water on the bottom. We're flowing up inside the shell, and then we're having our outlet on the top. So with having 15-pound steam, 15-pound steam is approximately 230 degrees. So we're basically going to superheat the water coming out of the heat exchanger. It can come out of there, somewhere like around 190 degrees. And what we'll do is we have redundant blending valves where so if you want the outlet temperature to be set at 140, the first blending valve is going to set it down to 20 degrees within that set point. So in this type of scenario, the first one's going to knock it down to 160, the second would be to 140. Since these things are constantly blending, we have extremely accurate outlet temperature control, which should not differentiate by more than plus or minus 2 degrees as long as we have constant flow going through it, which in most commercial applications you're going to have a building recirc type pump, which is going to give you that type of flow. Even if we don't have that, it would be plus or minus 4 degrees, which is extremely accurate compared to other steam water heaters that utilize a steam control valve, which the temperature fluctuation within those, especially in low flow conditions, can be extremely erratic. We do have redundant shutoffs, so we have T-stats in the system, so if one of those blending valves for some reason are not functioning properly, we can incorporate this into a building management system to sit there and say, hey, we shut this thing off, we need to take a look at the thermostatic control valve number 1. That could be because of scale buildup or anything like that we just need to maintain, clean out. It's a very simple process to do, and we can get that unit back up and running in an extremely short period of time. The other thing we can do with this unit is we can utilize the condensate coming off of it, which we'll go over here in a little bit how that functions, but we can use a condensate subcooler to preheat the water going into this heat exchanger to up the efficiencies of the steam heat exchanger. Usually a steam heat exchanger might operate in the low 80s when you do the calculations with how much steam we're putting into it with what we're getting out of it. With that condensate subcooler, we can actually get that to the low 90s, so we can bump that up by about 10%, if not more, in order to utilize our steam to get more hot water out of that unit. So the way this system works is we use an F&T trap. That's going to be the cork in the system. So if we're not flowing water, we're not transferring heat. Essentially that entire system will just fill up with condensate and it'll just plug itself. We're not using any steam. As we sit there and flow water across it, what will happen is now that we're flowing water across it, we're creating condensate. The F&T trap would function the way it's designed to, and we're creating hot water while controlling all the condensate that comes out of it. From a facility maintenance point of view, it's nice because we can clean in place. That's one thing that a lot of universities, hospitals, they really don't like maintaining a traditional steam water heater because of the amount of man hours and how hard it is to maintain the heat exchanger in it. Traditionally they might allocate an entire day to break down their steam water heater, take out the bundle, clean it, descale it, do all that stuff. With clean in place, it's a lot easier to do that. Basically what we do is shut down the unit with regard to steam, isolate it, let it cool down, and then we have 2 ports that we can hook our anti-scale product into. Most of the time it'd be like an anti-scale solution that you would just need a small pump and put it in a bucket, and you would run it across the heat exchanger to descale the heat exchanger. After a period of time, depending on seeing what you're getting out of that anti-scale flow, you can usually see it clearing up a little bit. You'll know you're getting most of the scale out. In that case, you remove that anti-scale pump and that anti-scale fluid, flush it out, get it filled back up with water, turn on the steam, click on the unit, and you're back making hot water again. So instead of taking an entire day it can take anywhere from a half an hour to an hour, and all you're doing for the majority of that time is just waiting for the pump and the anti-scale solution to do its job. So with regard to that heat exchanger, what we can also do is incorporate a storage water tank with that. And this is where we start getting into sizing things differently. So traditionally for an instantaneous steam unit, you're going to design that system for your max flow. So if you're designing that system and you're requiring, let's say, 120 GPM of flow, that's what you have to size your steam side requirements for, your steam side piping, your heat exchangers, and everything else. That can be very cost prohibitive, and if we can incorporate a storage tank into that design to take those dump loads and look at the way that that facility is using water with a little more scrutiny, we can drastically downsize our steam side requirements for that hot water system. The other thing we can do is with that heat exchanger design, we can incorporate redundancy into the same water heater. So we can have two heat exchangers on one rack, each one operating independently, incorporated with a single storage tank that has a 25-year warranty. So if you need to clean in place one heat exchanger, you can do that and still only reduce your recovery by 50%, because you're still operating off of the other heat exchanger until that heat exchanger and the preventative maintenance is complete. You start it back up and you can do the other one. So you're never out of hot water production. Now the design of this is different. So instead of having redundant blending valves, the way this operates is basically with a T-stat inside the storage tank connected to a pump. So as long as we're flowing water across that heat exchanger, we're creating hot water. If that pump stops, we're not creating any more hot water because there's no water flowing across that heat exchanger. So the way this thing operates, the T-stat drops below a certain set point, turns the pump on. It would open up the ASCO solenoid valve next to the F&T trap. When that happens, now we're creating hot water, we're creating condensate, the system's working just like it should. When the T-stat is satisfied, we will actually run that pump for an extended, like 1 more minute to 2 more minutes, which is going to fill that chamber or that shell back up with, or actually the tubes back up with condensate, because there's no call for hot water. So as soon as the storage tank is satisfied, basically after the heat exchanger is filled with condensate again, the pump shuts off, and we sit and wait until we have a demand for hot water, in which the system would kick the pump back on and would create more hot water. What this does also is it gives us the ability to raise or lower our temperature inside that tank. With the instantaneous COBREX unit with the redundant blending valves, our set point is fixed. So the second blending valve might be set at 140 or 150 or 120 or whatever you want that outlet temperature to be. We would not be able to adjust that water temperature unless you switched out that blending valve to a higher or lower set point. With this, you would be able to control the temperature inside the tank just like you would with any other water heater. It just depends on how long we want to run that pump and how much hot water we want to throw into that tank through the baffle diffusers. So the nice thing about this is there's no thermostatic control in it. We just have a T-stat and a pump, which, like I said before, that's going to allow us to raise or lower the overall temperature and outlet temperature that we're putting out into that building. So, like we said previously in a few slides, what we're able to do is go to a sizing chart. And I want to show you this really quickly. Basically, what you can do is look at your system demand in 15-minute increments. So we're looking at quarter-hour increments because you're not going to be flowing 100% for all 60 minutes out of the hour. And so we have different variables that you can throw in here, your inlet temperatures. So let's go worst-case scenario. We're looking at 40 degree. We want our outlet to be 140. We want our max GPM to be 120. So based on that scenario, we're going to ask or try and evaluate how often we're going to be flowing at a full 120 gallons a minute, as long as it adds up to 15. So in this scenario, we're flowing 120 gallons a minute for 2 minutes out of that 15-minute period. Out of that quarter hour, we're estimating that we're going to need 2 minutes of 120 gallon a minute flow. So at 50% load, we're estimating 3 minutes. At 25%, 7, and at 10, 3. So that all is going to add up to our quarter hour. With that, we can also go with our steam supply. We're going to say 15 pounds feeding it. If we want to switch this up, we can now kind of adjust our design based on number of tanks and the size of the tanks, or how many heat exchangers we have, which is going to govern our recovery. So based on this scenario, let's say we want to have, we'll say, 1 heat exchanger at 25 gallons a minute. Since I changed that, we have 1 tank at 300 gallons. Now, if I wanted to adjust this up to a much higher storage capacity, we might be able to get away with that much smaller GPM requirement. Now, if we wanted to sit there and say that this thing, we need to up this because we still can't achieve what we want to achieve. Let's say I want 2 heat exchangers at 25 gallons a minute because now I want redundancy on that rack system. As soon as I put that in, now we're able to sit there and drastically reduce our storage. So now we're recreating 2 heat exchangers at 25 gallons a minute for 50 GPM total with 300 gallons of storage. We're able to downsize our steam side requirements in this scenario by 63%. So in an instantaneous type configuration, we'd be using upwards of almost 6,400 pounds an hour of steam. With a COBREX storage, where we're splitting those between 2 25-gallon-a-minute heat exchangers with a small, 300-gallon storage tank, we reduce that down to just under 2,400 pounds an hour. So for your mechanical guys, that's drastically going to downside their steam side design and also reduce the amount of installation cost and steam consumption for that facility. Let's say we don't have the footprint for 300 gallons. Let's say we want to reduce it down to 150. Well, I can't do that now because in this scenario, we're not going to be able to make up the water demand for our recovery and the storage that we have on site. So in that scenario, we might need to increase our recovery of the units to 30. That didn't work. 40, yes, that worked. So now we have 2 heat exchangers that can do 40 gallons a minute with 1 storage tank of 150 gallons, and we can still satisfy the demand for that system. So basically, green means go, red means stop. So if I put this in and said I just wanted 1, it's going to tell me I can't do it. So it's a really nice and simple forward way to kind of size a steam and storage system and really giving that owner an option with regard to downsizing their steam side requirements and increasing redundancy in a much smaller footprint with our heat exchangers and our storage tank. Yes, sir.
Brett, if you can go down to where the tab down there where it says peak demand by industry on the toolbar, yeah. PVI has pre-calculated those 15-minute demand schedules for different types of job scenarios, and we guarantee that sizing, those diversity selections. So if engineers are looking for some guidance, there's some right there we've already done. There's also the Hunter's Curve tab there to calculate your instantaneous load, so you can plug it into your storage sizing calculator. And if you go back to the original page there, when you do all this, go up to the top, we actually, where it says the model selection, every time you fill in the yellow fields, it actually gives you a model so that you can get back with Brett and he can give you a spec sheet on that model.
That's a very good point. Thanks, Jim. So if you guys have further questions about the sizing, definitely give us a shout. We'd love to come in and kind of walk you through it. Let's see. So that's the steam side of things. You know, with regard to kind of an overview with that, we can incorporate redundancy and a large dump load into a single footprint. The COBREX type unit allows us to do that. And then we can also do that with boiler water. So the same type of approach that we used for COBREX and COBREX storage, we can do that with boiler water as well. We can do that with a brazed plate and frame heat exchanger. The same concept with upflow water, you know, cold water coming in, upflowing, hot coming out. We can get a 5-degree approach temperature on this design. And if you incorporate that, and we can clean in place just like we did with the COBREX unit. But if we incorporate that type into a storage tank, we can we can approach that as the same type of sizing scenario as the COBREX storage. Another benefit of this type of design is the pressure loss, you know, in your system. So if we incorporate this into with a storage water tank, you know, you're not going to see that pressure drop inside your system that you would traditionally see going through an instantaneous through a plate and frame heat exchanger. So it's a really, it's a basic system. It operates the same as the COBREX with a T-stat and a pump. It's just a different heat source. Instead of using steam with a steam heat exchanger, we're using boiler water with a boiler water heat exchanger. And, you know, this is really nice if you're using high efficient boilers, creating that, that boiler loop. You know, we can scrub a ton of heat off of that thing and return extremely cold temperatures back to your condensing boilers, which is what they want. So your entire design would function as efficiently as possible, including your hydronic boilers that you might be using. So basically that's all we have. So I've definitely gone over my 1 hour mark. Does anyone have any questions with what we covered? Or anything in general that you would like us to answer? So looks like I answered everything that you guys might have a question to. So, well, if you guys think of anything, please feel free to email us, and we'll absolutely get an answer over to you. We sincerely appreciate you guys joining us. Hopefully you guys found it useful and educational, and we look forward to working with you guys in the future. So,
yeah. Thanks for the great presentation, Brett, and thank you all not only for this class but for supporting Disney-McLane University in 2018.
Yeah, it's our last class, so
yeah,
we'll start up 2019 here soon. We'll be sending out the new schedule, and hopefully we'll see you guys in 19 as well.
Yeah, we're open to suggestions, too. If you got any suggestions for class topics next year, please give me an email or give me a call, and we'll talk about it. So thanks again, guys and girls, and have a Merry Christmas and Happy New Year.
Thank you, guys.
Thanks, Brett.